Welcome to this in-depth exploration of the neuro-symbolic loop. Our goal today is to rigorously examine the mathematical framework that bridges neural processing with symbolic logic. To guide our journey, we have four primary learning objectives. First, defining the canonical revision operator and its fixed points. Second, understanding Kleene approximants in the context of omega continuity. Third, contrasting computational reachability with semantic existence. And finally, analyzing the neuro-symbolic loop using the CSY metric. Specifically, you will learn how to formalize the iterative refinement of knowledge using lattice theory and how these symbolic structures interact with gradient-based learning. We are operating at a level suitable for researchers in artificial intelligence and mathematical logic, so we will focus on the interplay between monotonicity and the convergence of semantic interpretations. To understand the neuro-symbolic loop, we must first establish our mathematical workspace, the lattice of interpretations. Interpretation, denoted by capital I, is a mapping from atoms to truth values. Capital L represents the lattice of all interpretations, ordered by information content. The least element, denoted by the bottom symbol, represents a completely undefined state. The greatest element, denoted by the top symbol, represents a fully defined or contradictory state. And lowercase f is our revision operator. In this framework, an interpretation represents our current state of knowledge. We denote the set of all possible interpretations as capital L. We typically treat this as a complete lattice under the precision ordering. When we talk about the least element, denoted by the bottom symbol, read as bottom, we are referring to a state of total ignorance where no atoms have been assigned a truth value. The transition from one state of knowledge to the next is governed by the revision operator, lowercase f. This operator takes an interpretation and returns a refined version based on the underlying symbolic rules or neural constraints. A critical requirement for our operator is monotonicity. If interpretation I is less than or equal to j, then f of I is less than or equal to f of j. This ensures that as we learn more, we don't undo established logical consequences in a way that prevents convergence. Now, let's define how we actually reach a stable state of knowledge. This brings us to the canonical revision operator and the concept of Kleene approximants. Our learning objective is to calculate fixed points using the Kleene chain. In formal logic, we aren't just looking for any interpretation. We want the least fixed point. This is the smallest set of facts that are self-consistent according to our operator f. To find this, we start at bottom total ignorance and repeatedly apply f. This sequence is called the Kleene chain. We denote the nth iteration as f superscript n of bottom. If our operator f is omega continuous, meaning it preserves the least upper bounds of increasing chains, then the least fixed point, I star, is exactly the supremum or least upper bound of this infinite sequence. Think of this as a computational climb. Each step represents a finite amount of reasoning or neural inference. Omega continuity ensures that there are no jumps at the limit that the finite steps couldn't have prepared us for. In the neuro-symbolic context, this I star is the semantic ground truth that our neural network is trying to approximate through the loop. Let us ground these abstract definitions with a concrete, finite example. Imagine a small index set of three logical atoms, P, Q, and R. We define our revision operator f based on two simple rules: P is always true, and Q is true if P is true. We start at the bottom of the lattice, where all values are undefined or unknown. This is our zeroth approximant, I sub 0. Now we apply the operator f. According to our rules, since P is unconditionally true, the first revision sets P to true. Notice that Q remains unknown in step 1, because the rule for Q depends on the previous state of P. Applying f again, we look at I sub 1. Since P is now true, Q becomes true in I sub 2. If we apply f a third time, nothing changes. I sub 3 is identical to I sub 2. We have reached a fixed point, I star. In this finite case, the Kleene chain converges in a finite number of steps. The atom R remains unknown because no rule defines it. This illustrates computational reachability. We reached I star through a sequence of discrete logical steps. Now, let's contrast the finite case with an illustrative atomless schematic. This addresses the philosophical tension between semantic existence and computational reachability. In an atomless framework, we don't have discrete logical atoms like P or Q. Instead, information is spread across a continuum. Imagine a revision operator f that operates on a density function over this interval. Consider the operator f of x equals 1/2 x plus 1/2. We begin at an initial state x sub 0 equals 0. If we start at 0 and repeatedly apply f, we get a sequence: 1/2, 3/4, 7/8, and so on. Mathematically, the fixed point is exactly 1. It exists semantically as the unique value where f of x equals x. However, notice that for any finite step n, we never actually reach 1, we only get arbitrarily close. This highlights a gap. Semantic existence means the fixed point I star exists in the lattice. Computational reachability asks, can we reach I star in finite time? This is the core of the omega continuity requirement. If the operator is omega continuous, the semantic truth is the limit of our computational efforts. But here is the philosophical twist. In many neuro-symbolic systems, the ground truth might require an infinite number of steps to fully resolve. We must distinguish between the authority role, the ideal logic that defines what should be true, and our computational role, the actual neural network trying to simulate that logic. The atomless intuition suggests that our neural representations are often smooth approximations of these discrete logical limits. We now arrive at the core mechanism, the neuro-symbolic loop. This is the iterative process where a neural network's weights are updated to better approximate the symbolic revision operator. To measure how well our neural network n sub theta mimics the symbolic operator f, we need a metric. This is where the CSY, or token metric, comes in. Think of this as a weighted sum of the differences between two interpretations. Each token or atom, A, is assigned a weight W of A, often decreasing for atoms deeper in the logical dependency chain. This ensures that errors in foundational facts are penalized more heavily than errors in derived conclusions. Let's animate this loop. On the left, we have our table semantics, the authority. It calculates the next symbolic step, f of I. On the right, the neural network tries to predict this outcome. First, the symbolic table updates from interpretation I to f of I. Simultaneously, the neural net predicts n of I. The CSY metric measures the gap between the symbolic truth and the neural prediction. Finally, gradient descent pulls the neural output closer to the symbolic target, updating the weights theta. Initially, the neural network's predictions are noisy, but as the loop iterates, the network learns the logic. It's not just learning a static mapping, it's learning to simulate the process of revision. This is a subtle but vital point. By learning the operator f instead of the final result, the network gains the ability to reason over new, unseen facts. The loop essentially compiles symbolic logic into neural weights. This allows the model to internalize complex rules efficiently. In this final scene, let's consolidate our journey through the neuro-symbolic landscape by reviewing our notation and the core claims of the framework. First, let's look at our notation summary. L is the complete lattice of interpretations. Bottom represents the least information operator. F to the n of bottom is the n Kleene approximant. I star is the least fixed point, or the semantic limit. And D sub CSY is the weighted token metric. Our first major claim is that for a monotonic and omega continuous operator f, the semantic ground truth I star is the least upper bound of the Kleene chain. This provides a rigorous bridge between discrete symbolic steps and a continuous limit. Now for the core claims. 1. Convergence. I star is reachable as a limit of finite steps. 2. Authority. Symbolic rules define the correct f. 3. Approximation. Neural nets learn f, not just I star. And 4. Reachability. Some I star are semantically existent but only computationally reachable at infinity. The philosophical implication is profound. While the authority role of logic defines what is true, our computational role via neural networks can only ever reach a finite approximation. In an atomless or infinite setting, we are always approaching the truth. Let's review our learning objectives. We defined the revision operator and its fixed points, analyzed Kleene approximants and omega continuity, explored finite versus atomless examples, and visualized the neuro-symbolic loop with the CSY metric. We've seen how the CSY metric allows us to quantify the gap between our neural approximation and the symbolic ideal. By iteratively closing this gap, the neuro-symbolic loop enables a system that is both sub-symbolically flexible and symbolically grounded. This concludes our rigorous look at the neuro-symbolic loop. You now have the mathematical tools to analyze how neural systems can internalize and iterate upon formal logical structures.